Hello students, in today's class we are going to discuss about the Ohm's law. So far we have read about the electric current, what is it and how is it formed by the motion of electrons. Electron motion results in the electric current that is denoted by I, which is equals to Q into T, charge into time. Okay, so when we are going from the various materials, we find one thing, that is the rate of motion of electrons in conductor is very good, and hence conductors are named conductors because they are conducting the electricity. But in case of semiconductors, we have some other specific characterization, whereas when we turn to insulators, we see that these are the barriers to the charge motion. So when we deal with the conductor, why are we dealing only with conductor? Because we need to know the electrical property of a conductor, and when we go through the conductor, its shape, its size, everything matters. Like mostly we have seen in our household items, we use copper wires for the transmission of electricity. But sometimes we have seen the steel wires also and iron rods also at various other things, like the buildings made to save from the earthquake. We use the iron rods on the rooftop. Why? Because they have this particular area in it which helps them to conduct the electricity from the top to the bottom of earth by a mechanism known as grounding or earthing. The other one is earthing. Why is it so? Because more the area, more can the transmission go through. So this, can we say like these things are based on the area, on the size or height of the wire, everything? Yes, we can say. Then how is it related to the conduction of the current? So for that only we have this law which is stated as Ohm's law. Okay, this Ohm's law tells us about the differences or the dependence of the conductor's conductivity. So the terms in today's class which we are going to read or know is, one thing is conductor, related to conductor is conductivity, and related to conductivity is conductance. Opposite of conductance is resistance. Resistance is provided by the objects or the items or the equipment known as resistor. And opposite of our conductivity is resistivity. Resistivity. So these are the few terms you are going to get familiarized in this today's topic of Ohm's law. So we'll get start with the class. First thing is the Ohm's law. This law is proposed by G.S. Ohm in the year of 1828. This is a very basic law. So this law states, when current I flows through the conductor, V is the potential difference between the end of conductors, then Ohm's law is given by V proportional to I. Let's assume this is a conductor. Here we have some potential and over here we have some potential. So along the conductor the potential is V and the number of electrons are flowing through it, which gives us a current value of I. So the potential along this conductor is proportional to the current. If we increase the potential, current will increase. Increase the potential will increase the current. Okay. Now, if we are removing the proportionality sign from here, we'll get an equation which is V equals to Ri. Now, what is this R? R is the proportionality constant, which is known as resistance. Now we got a new term, that is resistance. In general English, resistance implies forcing back. Resistance is forcing back or stopping Like, just take one example. One superstar is there and you want to meet him. Now the superstar is covered with the bodyguards. These bodyguards will force you back or stop you from meeting the superstar. Okay, so these bodyguards are working as a resistor and providing resistance to your movement. The same is done by these resistors which we place in the electrical circuits. They resist the motion of electron in a given material, and hence what happens? There will be less motion of electrons and less conduction of current. So we got introduced with the resistance. Hope you know what does resistance mean now. Now R is resistance, whose SI unit is ohm. Why? Because Ohm found the Ohm's law, and by finding out the Ohm's law, he introduced us with this term of resistance. Okay, so its unit is ohm and its symbol is something like this. This is like a C, or you can say inverted U, which have two legs. Okay, inverted U having two legs. On a particular motion, you can make it like this. Okay. Now this resistance depends upon the material of conductor and dimension of conductor. Now how does it depend upon the material? If the material is a plastic, through which we are trying to make electrons move, through which we are trying to pass the current, we are providing a high voltage, will the plastic provide any motion to the electron? Basically no, no and no. Why? Because it's an insulator. Insulators have high resistance. They do not allow electrons to move, hence no charge. You can provide any amount of voltages to the plastic. There will not be any such changes. Okay. So it depends upon the material. Now if we see the metal itself, like copper, iron, aluminium, all these have different resistance. Though they have some resistance, it is minimalistic. Like if this is having some 11 resistance, value is 11, for this it will be 11.01, for this it will be 11.02. So slightly difference. If we are reading it on the micro levels, we can see these differences. But in case of we are reading them on the big scale, we will not be able to find such differences, and we'll feel that copper, iron and aluminum are similarly conducting the electricity, but it is not exactly the same. Now second is the dimension of the conductor. What is the dimension of conductor and how does it depend upon the dimension? We'll see. Like see, first is dependence of resistance on the dimension of conductor. For that, we'll do a little experiment and derive it. Once we will derive, the concept for us will become extremely clear. Okay. So just see, we are considering a conductor like this. See over here, this is a conductor. We have considered the cross-sectional area is A and length of the conductor is L. Written over here. It is a rectangular one, so we can call it a slab. Now we have placed two such slabs side by side to make a length of 2L. We will see on the next page the diagram. Like this is one slab and this is the another slab having length L and area A. Now the current is flowing through the slab is same. We passed a current Q through them. Okay. So similarly, voltage across the two slab is V and voltage provided is also same. We provided, like first of all we took slab 1 and slab 2 having the same area and length, then we provided same current and same voltage to it. Now voltage across the ends of combination is the sum of voltage of the two slabs. See over here, this is our slab number 1, slab 1, this is slab 2. Voltage provided across this is V, across this is also V. The current is I, the current is I. We have provided separately. Now the voltage total will be V1 plus V2 and the current through the combination is I and the resistance of the combination is RC. That is resistance across the combination. This will give us V plus V equals to 2V, but the current flowing through both of them, I total is I only. Okay. So what is the value of resistance? V equals to Ri. Then R will be V upon I. So for the combination of both, it will be R combination which is equals to 2V, V1 from here and V2 from here divided by the total current I. So combination's resistance will be 2 times the resistance of single slab. From here, from this particular equation, we have got this particular equation. RC equals to 2V upon I. Now hence doubling the length of a conductor doubles the resistance. This is very much important. So resistance is directly proportional to length. Resistance is directly proportional to length. Now the slabs is cut into two having length L but area A upon 2 each. What we did, we took a slab 1 with half of the cross-sectional area and we took slab 2 with another half of the cross-sectional area. Now length of the slab in both the cases is same. Length is same as L and we provided the voltage. Voltage across this 1 and voltage across this 2. Similarly, we provided current also. Okay. Now in this case, for the given voltage V across the length of slabs given, our current is I upon 2. If we are providing I current to the both slabs, one slab will take half of the current away and another slab will take another half of the current away. Okay. So area over here is A upon 2. Therefore, the next combination, second combination's resistance will be second combination resistance equals to voltage upon current. Voltage is V and current is I upon 2. It will be 2V upon I, which will give us 2R. Again twice. Therefore, if we decrease the area, resistance will increase. Halving the cross-sectional area of the conductor doubles the resistance. Okay. Resistance is inversely proportional to A. This is what we have given over here. So, this is, we can write therefore, increase the area to decrease resistance or vice versa. Now we will combine the equation, this one, equation number 1 and this equation number 2 to get a combined equation that is R proportional to L upon A. Now we will remove the proportionality constant. We will remove the symbol of proportional, we will get R equals to rho L upon A. R equals to rho L upon A. Okay. Now, what is rho? What is rho? Rho is the constant of proportionality. Rho is the constant of proportionality which depends upon the material of conductor and do not depend upon the dimension of conductor. Okay. See, what we have seen in the previous slide was that R is proportional, or we can say R is dependent. R is dependent upon material and dimension, but the resistivity rho is only dependent upon the material, but not on dimensions. Okay. So rho is our resistivity. As we have seen, this rho is opposite of conductivity. This conductivity is given by a symbol of sigma, which we are going to see. Okay, see over here, sigma equals to 1 upon rho, that is our conductivity. So, see, using Ohm's law, that is V equals to IR, we have got the value of R. What is R? R is proportional to length upon area. Removing the sign of proportionality, R is equals to rho upon LA. Okay. From Ohm's law, we have V equals to IR, current into resistance. Now we will substitute the value of R, that is rho L upon A. So the voltage will be in terms of rho will be given as I rho L upon A. From this equation first of all tells us about the relation, and then secondly it tells us about V being proportional to the current, resistivity as well as length. If length of the conductor increased, the potential will be increased, and similarly voltage is also inversely proportional to the area. Increasing or decreasing the area will oppositely affect the voltage. Okay. Now from here we will find the current density. Okay. Current density is a new concept which needs to be learned. So this current density is basically tells about current per unit area. Another thing which we can read about the current density is, it is given as current density is directly proportional to the electric field. Directly proportional to electric field. Okay, it is denoted by a small j and its SI unit is ampere per centimeter square. That is current per unit area. Okay, ampere per centimeter square. If E is the magnitude of the uniform electric field in the conductor whose length is L, then the potential difference V across its end is EL. V equals to EL. Okay. From here we can get the value of V. Potential difference across its end is equal to the electric field and the length of conductor. Okay. Now from this equation we will substitute the value of E. It will be I rho L upon A equals to EL. Now we will cut the LL because they are both same. Now the E equals to I rho upon A. Okay, now I upon A will give us a value of E equals to I upon A is J into rho. Okay, J into rho. Now the value of J will be E upon rho, which can be written as J equals to sigma into E. 1 upon rho is equals to sigma, which is conductivity. Okay, conductivity equals to 1 upon resistivity. Okay, so this is the formulation. See here, EL equals to J rho L, E equals to J rho, and here J, if we are taking J here and E here, it will be J equals to E upon rho. And if we substitute and follow up this equation, we will get the value of our current density. This equation gives us the value of current density. Now let's summarize the Ohm's law in the next slide so that you will have the whole total of the idea. See students, in today's class basically what we have seen is the Ohm's law. This Ohm's law was given by G.S. Ohm in 1828, and this states that voltage across a conductor is proportional to current in it. When we are removing the proportionality sign, we introduce the proportionality constant R. Proportionality constant. Okay. Now, this R is known as resistance. Resistance. This resistance is dependent upon two things. First is the material of the conductor. Other one is the other one is the dimension of the conductor. Dimension of conductor. Okay. Now the other thing over here is this resistance is dependent upon dimension. So when we are talking about the dimension of a conductor, we aim at introducing the two things. One is the area of the conductor, other one is the length of the conductor. So we have seen that our resistance is proportional to length and our resistance is proportional to 1 upon area. So it is a direct relation and this is a inverse relation. And when we are combining these two equations, we get a equation which is L upon A. Now we need to remove this sign of proportional. It will be rho L upon A. Again here we got the another proportionality constant, that is rho. Proportionality constant. Now we need to tell about the rho, what rho is and how it is useful for our understanding. So rho is known as the proportionality constant there, but is also known as resistivity. It is opposite of the conductivity. Conductivity is denoted by another sign, that is sigma. Okay, this is rho and this is sigma. Okay, now for resistivity it also depends upon something, but it does not depend upon another thing as in resistance. So it depends upon the material of conductor, but is not dependent upon, not on the dimension. Any dimension for a particular material will have the same resistivity, dimension of the conductor. Okay. if you are having this kind of conductor and this kind of conductor, both will have the same value of rho, but R will change in both the cases. Okay, now we got a equation that is R equals to rho L upon A, and we got another equation that is V equals to Ri. Now we will substitute the value of R into this equation. We will get V equals to rho L upon A into I. From here in this equation we got a value J, which is current density, which is written as I upon A. So we can say that current density is current per unit area with a dimensional formula of ampere per centimeter square. So substituting this into here, rho A into J. So voltage is equals to rho L into J, where J is our current density. Now we know that current density is directly proportional to the electric field. Directly proportional to electric field. So we will have another equation, and then we know another thing, that voltage is proportional to or is equal to electric field into the given length of the conductor, So keeping the two equations in mind, we will have a summated equation like, so we have this V equals to our rho L into J. Similarly, we have V equals to E L. Now we will equate these two equations. After equating, we will get rho Lj equals to EL. Here L and L will cancel and E will be equals to rho into J. So this is the relation between current density and electric field. Now next to it, what we're gonna get is rho is having another relation, that is rho equals to 1 upon sigma. Rho equals to 1 upon sigma. We have seen initially, right? Relation between conductivity and resistivity. Okay, so we will substitute this in this equation. To get a last and the formulated equation, that is E equals to 1 upon sigma J, which will give us J equals to E sigma. This is the formula for current density. Hope you got the class very well this time. This is all about the Ohm's law and relation of various factors with many other factors. Like what we have seen over this class, we have summarized everything. We have seen about R, V and I relation. We have seen the relation between V rho and I. We have seen the relation between V and E. We have seen the relation between sigma and conductivity. And then we have seen the relation between the voltage and the current density. And at the last, we have seen the relation between E and J, that is electric field and J. So in today's class, we have summed up and we have learned these many relationships and how these are related in a conductor. Upon that, we have read about the relation of R and sigma and their dependence upon the various factor of the conductor. Okay, So I'll close up this class with these information. In the next class, we will read little bit about the ohmic materials. Okay. And the derivation provided in this particular class are extremely important with respect to your board examination as well as for your entrance preparation. So go through all the derivation and try to solve by yourself, try to derive and try to read and learn these derivations. So have a good day. Bye bye.